Okay, so we did determinants, and just a little review from last time. We discussed the determinant of, well, maybe not last time, but a couple of times ago, the determinant of a 2 by 2, which is take the product of the diagonal and then subtract the product of the off diagonal. And then in talking about the determinant of a 3 by 3, we constructed this very wild formula, but we saw that in the formula there was a lot of 2 by 2 determinants. So this encouraged us to think about, to make notation easier, think about a new notation, M subscript ij, which we define as the matrix that's one less dimension that's formed by deleting the ith row and the jth column. So just for example, if this is your matrix, then can someone say what M, say 1, 2 would be? What would M1, 2 be? Good, yeah, D, F, G, I. So let's do that. So you take the entry 1, 2, and you delete the row and the column that it lies in. So you're left, what you're left over with is D, F, G, I. Okay, so we saw that we can turn this formula, this crazy 3 by 3 formula, to something that's a little bit more palatable. So it was the first entry times the determinant of deleting the of doing this matrix operation by deleting the first row, first column, and then we have this minus sign, and then we do the same thing. We go down the row and take the second entry and multiply it by the determinant of deleting that row and that column in position 1, 2. And then we go back to plus, and we take the last entry in the row, A13, and multiply it by the determinant of that matrix, deleting the first row and third column. So, so one thing I wanted to correct from last time, about the minor. The minor is not the matrix, but the determinant of the matrix. So the minor of the element Aij is the determinant of that matrix. So sorry, last time I said that the matrix was the minor, but the minor is just the determinant of the matrix. So the minor is a number. Either way, you can just take the determinant of that matrix. Any question? We'll do one more example, and then we'll kind of discuss more of other properties. But any questions just on those kind of basic notions of the determinant from last time? Okay, so let's do an example of a 3 by 3 determinant. Another example. Let's do 1, 2, -1, 0, 1, 3, 1, 0, 2. Okay, so our determinant formula. So sometimes when we do determinant, we do a vertical line on either side. So a matrix is usually either a square bracket or a parenthetical bracket. Well, determinant's usually like 2 straight lines, kind of looks like absolute value. So the determinant is A11 determinant of M11, then minus A12 determinant of M12, and then plus A13 determinant of M13. Okay, so let's refresh how to do it. So what's A11? So someone give me A11 and then someone give me the M11 matrix. So yeah, the M11 matrix is 1, 3, 0, 2, and A11 is 1. Yeah. So that's this entry here. Okay, so now let's go to the next one. So minus, so it's A12. Two. And then what's M12? Yeah, 0, 3, 1, 2. All right, please stop me if something doesn't make sense. And then what's A13? -1. And then determinant of M, what's M13? Yep, 0, 1, 1, 0. Okay, so any questions on the M's? Everyone see how we got the matrices there? Okay, great. So now let's do the determinant. So what's the determinant of the first matrix? So you don't give me the exact number, you just give me the subtraction. So 2 minus, but 3 times 0, which is 0. And okay, so what is the next one? What would a determinant of the second one be? Yep, 0 times 2, then minus 3. And then determinant of the final matrix, 0 minus 1. Okay, so we have 2 minus -6 minus -1. 2 plus 6 plus 1, so that's 9. Okay. What do we know about the first one, of this one here? Yeah, so the determinant of the 2 by 2 is, you take the product of this diagonal entries, and then you subtract the diagonal of the product of the other entries. So in our example here, 1, 3, 0, 2, we have 2 times 1 minus 3 times 0, which makes 2 minus 0, which is equal to 2. Sure. So it's the same thing for the, for the other, I don't know what happened there. For the other entries, other matrices. Yeah, you have a question? How do the M's work? Sure, yeah. So yeah, M12 is probably the harder one to see. So we define these M's like you look at A12, and then you delete that row and that column. So they just disappear. And the matrix that's left over, so it's harder to see because it's kind of cut in the middle, but think of like this will be your first column and this will be your second column in the new matrix, in the M12 matrix. Yeah, great. Okay, any other questions? So after all these calculations, we find that the determinant is 9. Does that tell you anything about the singular, non-singular aspect of this matrix? It's non-singular, yeah. So matrix is non-singular. What would tell you a matrix is singular? If the determinant is 0. Good. All right, so let's think about some determinants of some nice matrices. Correct, yeah, singular means it has no inverse. So one thing you could do, like when you're tasked to find the inverse of a 3x3 matrix, one thing you could do once you get more comfortable with determinants, you could find the determinant first, and then if it's 0, then you can just stop your work there. Is there an easy way to get the inverse of a 3x3, like 2x2 inverse? Well, our easy way is we do the row reduction to identity, which is pretty satisfying, I think, in terms of easiness. When you get to higher dimensions, you might want to have a nicer formula, which there are some out there, but it involves some other kind of aspects of matrix algebra that we don't really go into just yet. But what's nice about this property, this definition of or method for finding the inverse is that it relies directly on row reduction, which is very intuitive. So this is a very intuitive approach to row reduction and row equivalence. Maybe later in the course we could talk about a different formula, but it's not as directly intuitive from what we've been doing. It's kind of, this is the natural introduction to an inverse through row reduction. But yeah, but there are other ways, but with what we've been doing, we'd want to do row reduction just for the rhetoric of the course. But yeah, it does exist. So let's do some determinants of familiar matrices. Okay, so let's work in 2x2. What's the identity matrix in a 2x2? Yeah, 1, 0, 0, 1. What's the determinant of this? One. Yep, 1 times 1 minus 0 times 0 is equal to 1. Let's do the identity for 3x3 and look at that determinant. Okay, what do you think it is? So let's read it out. So what would, using our formula, what would it be? So what's the first thing we do? So someone give me the correct, yeah. So it's 1 times determinant of 1, 0, 0, 1. If the determinant of 3x3 is not 0, what do we do? This one was not 0, right? It depends on the question. The question is just find the determinant. The term being 0 or not 0 just says if it's singular or not singular. Correct, yeah. So the first one incorrect. We can ignore the rest because these are 0. So if you want to write it out, the next term would be 0 times determinant of something, right? But who cares? And then plus 0 times determinant of something, but who cares? Yeah, what is the who cares? For practice, it's 0, 0, 0, 1. And then what's the who cares for the last one? It's 0, 1, 0, 0. Yeah, it will continue for all n by n. We haven't discussed yet like 4 by 4 and above, but we will come back to this and see it'll be true for all n by n. Okay, cool. So so far the determinant for the identity matrix and for 2 by 2 and 3 by 3 is 1, which is kind of nice, right? You'd want like the identity matrix to be associated with 1 somehow. Okay, so let's do some other familiar matrices. Let's do the row swap for type 2, or for 2 by 2. Okay, what's the determinant here? Good. 0 minus 1, it's -1. Now let's do good practice. Someone tell me the row swap matrix, row 1 swap row 3 for a 3 by 3. What's the row 1 swap row 3? Yeah, the determinant's gonna be negative. Here it is. Yeah. Yeah, so 0, 0, 1, 0, 1, 0, and 1, 0, 0. Good. This is the row 1 swap row 3. Now let's do let's calculate the determinant. So what do you think? There are a lot of zeros here, right? So a lot of things can just cancel out. So we have 0 times something, but who cares? Minus 0 times something, and then plus 1. And what's the M matrix for the last one? What's M13? 0, 1, 1, 0. Yeah, 0, 1, 1, 0. Okay, so what's the result? So -1, yeah. So we just found out the determinant of this row swap was always -1, and then times 1. So it's -1. That's also pretty satisfying, right? All type 1 matrices right now. I mean, you can do the same thing for row 1 swap row 2 and row 2 swap row 3, but it's going to be this way for the other row swaps. It's always -1. That's pretty satisfying. Yeah, I got a question? If it's a row swap, will the determinant be negative always? Well, these are, right? These are row swaps. We'll then, after going through these, determinants, we'll talk about how do row swaps affect the original. Yeah. But it depends, right? If the determinant of the original matrix is negative, then row swapping it will make it positive, right? But we'll see that. We'll do an example where the determinant of the original matrix is negative and then we row swap it. Right, it just depends on the matrix. Yeah, so let's just do a type 2. First of all, what row operation is this? What type 2 row operation is this? Yeah. So what are you multiplying? Which row are you multiplying by? Yeah, and then which row are you multiplying by alpha? Row 1, good. Okay, so let's do the determinant. What is the determinant? Alpha. Alpha times 1 minus 0 times 0 is equal to alpha. So based on this pattern, we kind of expect for 3 by 3 that this determinant will be alpha. So let's check. All right, so again, these elementary matrices are nice because we have a lot of zeros, so a lot of terms you don't have to calculate. All right, so we have 1, and then what matrix is what's the M11? Yeah, alpha 0, 0, 1, and then we have plus 0. Okay, so similarly, the determinant is just alpha. So, and then can someone say what's the row operation for this matrix? Yeah, row 2 to alpha row 2. All right, now let's do 3 by 3. That's where things are type 3. So this gets a little interesting here. So someone tell me for a 2 by 2, why was it in the middle? I just chose it to be there because I want to do row 2 times alpha row 2. But remember, alpha could be anywhere on the diagonal. Yeah, just wanted to change it up. Someone tell me the row operation that does, let's do row 1 to row 1 plus alpha row 2 for a 2 by 2. What does the matrix look like? Good, 1 alpha 0 1. But just be aware, on the midterm, I might give you a row operation. You will tell me what the matrix looks like, and I might give you a matrix and you tell me what the row operation looks like. So just be aware. Make sure you're able to do this. Okay, now what's the determinant? Yeah, so it's 1 times 1 minus alpha times 0. So it's 1. Huh, that's interesting. Kind of wouldn't expect that, right? You're adding a multiple alpha, right? So you'd think there might be alpha involved in here, but no, it's just 1. Let's to make sure we're let's do the other row. What's the determinant of that 3 by 3 or 2 by 2? Also 1. That's interesting. So determinant of a type 3 is 1. So let's see the same thing applies for a 3 by 3. All right. Someone give me the matrix that does row 2 to row 2 plus alpha row 3. Someone give me the first row. 1 0 0. Someone give me the second. Good. 0 1 alpha. And the third row 0 0 1. Okay, so let's do this. So what is it? It's 1 times 1 alpha 0 1 plus 0 plus 0 and also 1. So I think this is kind of the most surprising thing is that the type 3 operations, which are probably the most involved operation, has the most simple determinant. Okay, so now let's do the same deal And now let's see how these elementary operations, how they affect matrices. Now this is what someone was asking before, how do row operations affect the determinant of a matrix? So let's do, so we did this one, we were doing this last time. So when you do a row swap, it's C, you swap the rows, and what's the determinant of CDAB? What's the determinant of CDAB? Yep, CB minus AD. Good. So, and what is the determinant of ABCD? It's AD minus BC. So what is CD minus AD to AD minus BC? How do these two compare? Negative. So if you factor out a negative, get negative AD minus BC. So these for 2x2s, and you can do the same for 3x3s. If you row swap a matrix, the determinant gets negated. All right, so let's do alpha 0, 0, 1 times A, B, C, D. Okay, so this is multiply the first row by alpha. So we have alpha A, alpha B, and then C, D. Okay, what's the determinant of this? Can someone read out the subtraction? Yeah, so it'll be alpha AD minus alpha BC, and then you can factor out an alpha with AD minus BC. And again, this is the determinant of AD BC. So you can see that maybe multiplying a row by a number multiplies the determinant by a number. So let's think about actually, can we, so does it make sense that 1 over alpha times the determinant of alpha 0, 0, 1, A, B, C, D is equal to the determinant of A, B, C, D? Does that make sense? So I'm just I'm solving for a determinant of A, B, C, D. Does that step make sense? So yeah, so I'm just dividing by alpha on both sides. Okay, and then type 3. Let's do that. And so what's our matrix going to look like? So what is this row operation? So remember, you don't need to do the multiplication if you know the row operation. So the row operation is what? 1, 0, alpha 1. It's not a type 2. Alpha row 2 would be a type 2 operation. The negative would imply Let's talk about an inverse. Other way around though, row 2 plus alpha row 1. Right, so if you know that, you don't need to do the multiplication. So it's just C plus alpha A and D plus alpha B. Okay, so let's see what the determinant of this is. So it's A, D plus alpha B minus B, C plus alpha A. Everyone see that so far? Let's multiply it out. AD plus alpha AB minus BC minus alpha AB. What's that? Can you do anything to that? Can't. So that's nice. So the determinant, when multiplying by a type 3 operation, does not change the determinant. Okay, so now bells and whistles should be going off in your head right now. So you should say, okay, determinants are so easy now, right? If I can just do row reduction, then so if I have a really complicated matrix and I don't want to calculate all these determinants of these 2x2s, I can do row reduction and maybe restrict myself only to type 3s and then construct a matrix that's very easy to find the determinant of. Does that make sense? So 2 matrices that differ, yeah, I will, only by type 3 matrices have the same determinant. So that's pretty remarkable. And again, if you want to do type 2 operations in there, you might have to think about dividing. If you do type 1s, you might have to negate, but type 3 operations are very nice because they don't affect the determinant. So let's do an example. Okay, so why is this, why is a matrix like this? Let's do some nicer numbers. So this is a nice candidate of using type 3s to calculate determinant. Is that I can construct zeros, right? Zeros, when calculating the determinant, are very handy because they can make calculations a lot easier. So for example, we can, if we eliminate these first 2 entries, we have a lot less things to worry about. Okay, so let's do it. How do you delete those 2 entries? Yeah, I'll make it a little even easier. Yep, row 2 minus 2 row 1. And how do you delete the last entry? Row 3 to row 3 minus 3 row. So it all comes down to row reduction in the end. So 0, 1. So -6 makes this -7. 0. -3 makes this -2. So -9 makes this -7. That's correct, right? Okay. All right. How could you continue row reduction? It's another nice 0 that you can do. Let me just get rid of that one. Oh, you could do that too. I'm just thinking like in terms of our row reduction. So let's do this one just because we want to do for doing type 3s, and we'll just see what happens. So how do you get rid of the -2 there? Yeah, row 3 plus 2 row 2. 1 is -1. Sorry, this one? I have 3 and then -2 times. Oh yeah, I'm sorry. I changed the numbers around to kind of make it nicer. Sorry. Yeah. Yeah, my bad. Okay, plus 2 is 14, so it's -21. And not a full column of zeros there. Okay, everyone see that? Okay. Now let's find the determinant. You can do more, but for what we're going to do next, let's find the determinant of this. So we've only used type 3 operations, right? So while we're here, actually, so what would happen if I did, what type 2 operation would I do to make this easier? What's a very annoying number here? The -21, yeah. What would you do to that row to get rid of the -21? Divide, yeah. So if I do row 3 to 1 over -21 row 3, how does that affect the determinant? So when I do the division 1 over -21, how is the original affected? Right, it gets divided by 1 over -21. So what I could do is if I multiply by -21, then the determinants are the same. Does that make sense? So if I didn't have this -21 here, then the term of that matrix will be off by a factor of -21. But if I multiply by, does that make sense here? So these determinants are different, right? Right, it's off by a factor of -21. But if I offset it by multiplying by -21, then the determinants will be the same. This is this. So if you do a type 2 operation that multiplies a row by a number, you can offset it by dividing by that number. So this row operation multiplies by 1 over 21, so I can offset it by dividing to make up. Any questions on that? Everyone see what we're doing? Yeah, I'm just, because I want to keep the determinant the same as this original matrix, right? It's 1 over 21. So in this matrix where this is multiplying, let's say multiply by negative 21. So what you do is, or no, we're not multiplying by negative 21, multiplying by 1 over negative 21, right? So how do you make up for multiplying by 1 over 21? This is 1 over negative 21, which is equal to negative 21. Yeah, so here's the matrix A, B, C, D. This is the analog is this. Here's pretend this is A, B, C, D. Right, these are the same. So if I multiply that matrix by, if I multiply a row by alpha, I'm multiplying a row by alpha, then the new matrix will be off by a factor of alpha, right? So if I multiply by 1 over negative 21, does that make sense? See how the math works? Yes, here. So does this statement make sense here? Okay, so let's say we're doing this. So we're doing, this is what we're doing. 1 over negative 21. 1 0 0 0 1 0 0 0 1 over negative 21 times 1 1 3 0 1 negative 7 0 0 negative 21. So this line right now is the same as this line. You see how the two lines are the same now? This is the A, B, C, D line. This is the 1 over alpha line. This is alpha 0 0 1 line, and this is the A, B, C, D. Or this is yeah, this is the A, B, C, D. Yeah, so if you divide a row by a number, to offset it, you multiply. What's 1 1? Sorry, I don't understand your question. Nothing. Okay. So again, so just to reiterate, so if you it's confusing because it's division. If you multiply a row by a number, to offset it, divide by that number to keep the same determinant. So what we get is negative 21 times this matrix, the determinant of this matrix. I think you can tell me, what is the determinant of that matrix? I think we all know that, actually. What's the determinant of, without the negative 21, what's the determinant of that matrix? So think about what determinant means, what we've said about row operations, and there was one matrix that we found that had a nice determinant. So let me ask you, so remember, Yes, it's 1. Why is it 1? Well, we can do it, just look at it, right? We don't even do um, the formula. Can you eliminate these entries with row reduction? Do you see how those entries can be eliminated using row reduction? Remember, think of reduced row echelon form. Good. Now, what elementary matrices? Correct. Yeah. You only need type 3s to delete these. So we said that type 3s do not change the determinant. So that means the answer is -21. Because then we get, this is row equivalent using only type 3s to identity. Okay. Any questions on that? Yeah, that's a consequence. Yeah, the answer is just -21 in this case. Yeah, that's a consequence. If a matrix can be put into, let's say, can be made, yeah, the solution, the determinant of the last matrix was -21. If a matrix can be made into identity using only type 3 operations, then the determinant is 1. Yes, that's a consequence of using type 3 operations. Okay, can you tell me when is a matrix singular? Okay, when determinant is 0, when else is a matrix singular? When it's not row equivalent to identity yet. Okay. How do you know if something is not row equivalent to identity? What form of a matrix tells you about row equivalence to identity? So we'll subsection of being row equivalent to identity. What form of matrix do you want to look at to determine if it's row equivalent to identity? Something I was looking for is reduced row echelon form. The reduced row echelon form is not equal to identity. Okay. Can you give an example for an n by n matrix whose reduced row echelon form is not identity? Like, what's a property of a matrix that has its reduced row echelon form not identity? When it's n by n, yeah. So if you have an n by n matrix that is not, you calculate its reduced row echelon form and it's not identity, what do you know about the matrix? Like, what does it look like? Sure. That's what I was looking for, yeah. You must have a zero, at least one row full of zeros. There has to be at least one row that's full of zeros. So you could have like something here, something here. We know if all of these three entries are not zero, then it has to be row equivalent to identity. So at least one of these things must be not zero, must be zero. So at least one row is full of zeros. So we just showed that row reduction, kind of keeps some property of the original matrix, of the term of the original matrix, right? Type 1 at most type 1s multiplied by -1. Type 1 ops multiply by -1. Type 2 ops multiply by a number, non-zero. And what do type 3 ops do again? What do type 3 operations do to the determinant? Yeah, just nothing. Well, not nothing, but multiplied by 1. Doesn't change. So do you see how if you have a row full of zeros, and it's not row equivalent to identity, so how to determine if a matrix is singular, you can do a row reduction. And so here's what I'm saying. So if you have a matrix and you do some row operations, and it's equal to reduced row echelon form with a 0 row, then you know by what it means to be non-singular that this is determinant 0. And the only way that a matrix is singular if its reduced row echelon form is not identity. So any matrix must. So if you have a matrix with a row full of zeros, then it's determinant 0. So this is a way we can identify just by looking at a matrix. If you have a row or a column, it would also be true for a column for reduced row echelon form. Then the determinant is 0. So again, we can use this property of row operations, how they affect determinant, to give a precise condition for singular matrices. That if you have a row full of zeros, then the determinant is 0. Or if you can row reduce to a row full of zeros, then the determinant is 0. Okay, so let's think about expanding our notion of determinant to higher dimensional matrices. So just recall, so we have our minor as the determinant of, let's say, minor of Aij is the determinant of Mij. So it's this deletion of the ith column, ith row and jth column. And we know that everything in our determinant of a 3 by 3 is always of the form A, or maybe this -1 thing to the k plus 1 of a 1k determinant of m 1k. So to put this into a more general form, let's clean up this definition and call this one thing. Let's call this A1k. So it's a formula. We're going to call A1k equal to -1k plus 1 A1k determinant of M1k. Is that okay? I'm just replacing that whole term by A1k. Big A. Everyone okay with that? It's just, I'm just substituting. So I'm using a capital letter with subscripts for this substitution. Everyone okay with that? Yes, no, maybe? So the determinant of a 3x3 matrix now, we're saying is k equals 1 to 3 of A1k. So where A1k is defined as this -1 to the 1 plus k of A1k determinant of M1. So this will be called the cofactor of A1k. So why is this a preferable maybe definition? It just makes it look a lot more clean, right? You just have one thing that you're summing up, and that's the formula for that one thing you're summing up. So expressing the determinant this way, when we say determinant of A is equal to k equals 1 to 3 of A1k, this is called the cofactor expansion of A along the first row. And this second statement doesn't really make sense now because every determinant right now is in the first row. We'll find out that we can use any row or even any column. So the question is, let's say if A is 4 by 4, what is the determinant? Okay, so let's imagine doing this, and we have this 4 by 4 matrix, let's say, and you tell me, based on some stuff that we did today, what could you do to this 4 by 4 matrix to make it easier? Because remember, what is a property of a matrix being non-singular? So I'm going to just regurgitate that back because it's really important to know. When is a matrix non-singular? You can turn it into the identity. Yeah. Oh, that's singular. Singular is when the determinant is 0, non-singular when the determinant is not 0. So the big thing is you can turn it into identity is non-singular. So we're going to do a similar trick that we did for the 3 by 3. And well, let's pretend we did one operation of row reduction. So the first row reduction operation would be to delete the entries in the first column, correct? I probably shouldn't use O for letter. Let's say Q. So now look at this. what could you tell me is what makes this 4x4 non-singular? How would you know this 4x4 is non-singular? So remember, try to recall the proof of the 3x3. How is this 4x4 non-singular? What do we do in the 3x3 proof to say something about the 3x3? You remember what we did? What must be true about this 3x3? Correct. I want to look at the determinant, right? If determinant of the 3x3 is not 0, then the 4x4 is non-singular. If, what is one other condition we need? So if the determinant is non-zero, so if the 3x3 is row equivalent to identity, what must else be true about this matrix? So pretend we can do that. We have row reduce this to identity. What else must be true? What else must be true? If A is not equal to 0. So I could say that the determinant of this 4x4 in this form where we have is A11 times the determinant of M11. Does that make sense? If both of those things are non-zero, then the original matrix is non-zero. Does that make sense as a way? Yeah. So now, why don't I care about these entries? Because it didn't matter, right? It didn't matter for these entries. So why don't I just put it in anyway, right? If I have, and you tell me why it doesn't matter. And to A12 determinant of M12, why does M12 not matter? Why is it okay if I put this in the formula? Think about M12, M13, and M14. Okay, what are these? What do these look like? Or not the determinant, but what do the matrices look like? M13, M12, M13, M13. Yeah, what do they always have, these entries? They have a 0 column. Right. So it's okay to put them in the formula now, right? Because they're not contributing anything. So we're out of time for now, but so next time we'll expand this to n by n. If you know induction, it's just a matter of, it's just that. But right now we have our formula now is, you can think of A1K, determinant of M1K, with this -1 thing, 1 plus K, and K equals 1 to N, or K equals 1 to N of big A 1K. Okay, so so next time we'll maybe kind of talk about this thinking about for arbitrary matrices, and why this is also true. That you can do it along any row and any column. You said if an entire row is full of 0, it's singular. Same thing, it's also 0. Notice that the reduced row echelon form, if you have a column full of zeros in the reduced row echelon form, it can't be a row equivalent to identity, right? Right, so both of those imply the same thing. Sure. And being row equivalent, so big takeaway from today is, how do you make finding determinants easier? Do row reduction. So next time, we'll even say, like, I would think about yourself, like, what do you think the determinant of a triangular matrix is? Of a diagonal matrix? Maybe think about what we did in this problem here. So yeah, try working that next time, and we'll prove that. There's a nice formula for when a matrix is diagonal or triangular. Okay, so I'll see you Wednesday, finish up. And then we have our midterm next week. Okay, I'm gonna stop recording.